So we'll solve one problem now. So this is the truss which is given here, ABC, and the dimensions AB, BC and AC respectively are 6 meter. So you can see as the three sides are equal, this is an equilateral triangle. So this angle is 60 degrees and this is also 60 degrees. Now we have to find out the forces in AB, BC and AC. So we will be using or we will be solving this by using method of joints. So the first step in solving this numerical is finding out the reactions. So we have to find out the reactions. So joint A, at joint A, hinge support is present. So hinge support has two reactions, vertical and horizontal. So vertical VA, horizontal HA. Similarly at B, there is a roller support. Roller support has one reaction, that is VB. So first we have to find out HA, VA and VB. So we'll be using sigma Fx is equal to 0. That will give us HA is equal to 0. Then sigma Fy is equal to 0. So this will give us VA plus VB is equal to 1. Then we'll be using sigma MA is equal to 0. Sigma MA is equal to 0. So this will be 1 into 3 is equal to VB into 6. So VB will be equal to 3 by 6, that is equal to 0.5. So VA will be equal to 0.5. So with this we can say here that this HA is 0, VA is 0.5 kilonewton and VB is also 0.5 kilonewton. One thing to note here is this structure is symmetrical. Okay, the loading is also present at the center. So directly you can divide this 1 by 2. So 0.5, 0.5 and that will be the reactions. Okay, now the next step is to consider each and every joint. So in the second step we will consider joint A. So now we will be considering joint A. So we will draw here, this is joint A. What are the forces which are acting here? So this is VA which is acting 0.5. Then HA is acting, but that is 0. The HA value is 0, so no need to show it here. Then there will be one force which is acting in this AC member. So this is FAC. Similarly, there will be one more force which will be present in the AB. So here it is FAB. What is this angle between FAB and FAC? 60 degrees. Now we need to solve this. So to solve this, we have to use a concept which is called as resolution of force. Okay, so resolution of force. This is called as FBD of A. No need to write it, you just have to draw it. Just for your information, I am saying it. Okay, so first you have to resolve this FAC. So first we'll draw the remaining things here. This is FAB, this is 0.5. Now if we resolve this FAC, there will be two components. One component in vertical direction, FAC sine 60, and one component in horizontal direction, that is FAC cos 60. Okay, now this is the main diagram that on which we have to apply the two conditions of equilibrium. Okay, so now first condition is sigma Fx is equal to 0. So apply sigma Fx is equal to 0. So what it will be? FAC cos 60 plus FAB, this is equal to 0. Similarly, second condition is sigma Fy is equal to 0. So that will give us FAC sin 60 plus 0.5 is equal to 0. So with this we can find out FAC. So FAC is minus 0.5 by sin 60. 0.5 by sin 60. So this will be minus 0.58. So now we have got the value of FAC is equal to minus 0.58. Now substitute this value of FAC in the equation number 1. So we'll get it minus 0.58 cos 60 plus FAB is equal to 0. Okay, in this equation we are substituting the value of FAC. So we will get the value of FAB. So FAB will be coming as 0.29 kilonewton. So this is coming as positive. That means whatever the directions we have assumed, among that FAB, okay, so this FAB is same and this value is 0.29. However, the direction of FAC, it is minus 0.58. That means this direction is not correct. So we'll change the direction now, and this direction will be, or rather than doing it here, what we'll do, we'll directly write it here, minus 0.58. After you find out both the forces, you write down the direction of joint A here. So this is 0.29 and the another direction is 0.58. Now one thing to note here is that with this you cannot directly decide whether the members are in compression or tension. The forces which you are representing here are the forces on the joints. These are not the forces in the members. So to find out what are the nature of forces in the members, you have to remember this sign convention. So this green color which I have denoted here, these are the sign conventions for the forces on joint, not on the forces in members. Whereas the red color which you are seeing here, red color markings, this will show us the nature of forces in members. So if you see the member AB, you can clearly see that member AB is under this kind of forces, and this is nothing but the tension. Okay. Similarly, if we draw for FAC, it will look like this. So for member AC, the red color markings show a compressive nature. Okay, so this is under compression. Now the same kind sign conventions you have to follow for joint B also. So we'll consider joint B now. Consider joint B. So on joint B, there is one force here 0.5. Then there is this red force, or you will change the direction here so that there is no confusion. This green color forces, these green arrows shows the forces at the joints. Okay, whatever the forces that joints are applying on the members, that are those forces. Okay, this is a point of confusion, so make sure that you understand this properly. Okay, now so on this side there is force FAB, the direction is green direction, and the value of FAB is 0.29. 0.29. So the last thing that is remaining is the member FBC, and this angle is 60 degrees. So now we'll resolve this. So if we resolve the force FBC, so this is 0.5, this is 0.29. This FBC can be resolved as FBC sine 60 and FBC cos 60. So with this now we'll apply only one condition, that is sigma Fy is equal to 0. So with this FBC sine 60 plus 0.5, this is equal to 0. So FBC is minus 0.5 by sine 60. So FBC is minus 0.58. Now you can see that this direction of FBC is coming as negative. This direction here is coming as negative. That means whatever direction we have assumed here, that is not correct. This value is minus 0.58. So instead of writing this, we can write it like this. this is B, 0.5, 0.29, and this is the direction of the force. Okay, and the value is 0.58. Now the same direction of FBC, you have to write it in the diagram or draw it in the diagram. So you can see it is towards the joint. It is towards the joint B. So this FBC, this is towards the joint. So if it is towards the joint, now the member will be in compression. Now directly by looking you can see all the values in the members. So this is 0.58 and this is in compression. This is also 0.58 and this is in compression. This is 0.29 and this is in tension. Okay, so all the forces in three members are calculated. Now properly you have to show this in one table, and that table we call it as a force table. So the last step for any truss problem is to draw a force table. So in this you just have to write these three things: whatever are the members, what is the value of force, and what is the nature of force. Okay, so here the member is AC, AB and BC. So 0.58, 0.29 and 0.58. The nature is compressive, tensile and compressive. Now this was a very basic problem in which there only three members were present. In the next video we will be taking one complex problem which will be having more than three members. The only thing we have to understand here is we have to take a joint one by one and then apply the two conditions: sigma fx is equal to 0 and sigma fy is equal to 0. Okay.